Thank you so much.
Mira,
Thank you. Thank you, ma'am. Am I audible? Am I audible? Am I audible? Am I audible? Yeah, thank you. Very good morning to all. Good morning, very good morning to one and all dignitaries on the dais and my old friend, Principal Dr. Suhas Kok, and my friends, Professor Handori, Aishwarya Gawan, and Head of the Department Sahani ma'am, and Asha Jadhav ma'am, and all other my fellow colleagues and participants. First of all, I congratulate and appreciate all the effort taken by the KJ team KJ team by principal, the head of the department, and the FE team together for organizing this workshop consistently for the second time. It's a very good initiative. Congratulations, and I real my heartfelt appreciation to all of you. And it's indeed great pleasure for me to be a part of this program. And thank you very much, Coach Sir and team, for inviting me for this FTP. I, I'm sure that my fellow colleagues and participants will have a knowledge immersive journey to explore the profound impact and latest research development of mathematical principles and techniques in the emerging areas of scientific development and further technological innovation, leading to further technological innovations. The entire scientific community is undergoing a paradigm shift related to the techniques and methods and applications after the emergence of AI. A new AI world is emerging. So here, the mathematical thinking, mathematical logic is going to play a very important role. So we have a big role to play, like Professor Kotzer said. We do have a big role to play in the new emerging areas of AI. So where we need to ask, so we are not competing with the machines here. We need to have extraordinary skills and competence to what machines cannot do. So their mathematics play a big role. So, and, coming to all mathematical, to all the fraternity related to the mathematics, we have many questions which coming to our mind. Do we have to discard our age-old traditional mathematics, or do we have to learn new softwares every day, or new technologies are coming up daily, or do we have which technology to study? How do we combine both the things? So there are many questions which comes today in our mind. One person says this, one person says that. Then what we need to follow? We need to listen to everyone, and we need to develop, find our own path. So for that, I have one the new mantra which the whole world is following: the upskilling, reskilling, and skilling. So, and in mathematics, this is what we need to develop. That's what my research or my reading says. So let me come to the first thing, reskilling. So the traditional mathematics has to be now reskilling. So here the my first question: do we have to discard the age of mathematics? Absolutely no. So we need the traditional mathematics as a role to play. It has a new shape has to take over in the emerging era of AI. For example, I'll just give one small example. Like we always classify our differential equations as ordinary differential equations and partial differential equation. And recently, for the last 30 years, we have added fractional differential equations too. Now, for the last 20 years or the 10 years, a new classification of differential equation has come. That is neural differential equation. Differential equation has emerged, has combined with AI tools that provides a way of it's a bilateral, it's a bidirectional graph I can see. AI tools are used to solve differential equation. Differential equation solutions play a major role in shaping AI or finding new algorithms. So neural differential equations are coming up in a big way, and it is going to that's going to be the another research area for the next 20 years. So we can say that it's nothing but, I was wondering what is this all about. It's nothing but we in finite element method we do a grid computing. This is nothing but a meshless computing for all our differential equation techniques. So this is one open area of research for all of you to work on, neural differential equation. That's how this is just one of the area which is coming up. The another thing which I said is upskilling. Upskilling, what is this upskilling? So there my second question come. New tools and techniques, new emerging softwares are coming up. We all are familiar with C, C++, Python too. So now we need to develop the we need to upskill our technology to understand the methods of the emerging software tools too. We don't have to master it, but we should know how to apply it. And we need to understand how our mathematics is different from how we can combine to get the best result, and where the software fails and our role starts. That also we need to understand. So we can talk on that provided we know to implement that. Okay, so we also should be familiar with Anaconda, Jupyter, Python, all the tools and techniques. Then comes with uh, and the in the upskilling technique. I was just going through one of the areas. Whole world is coming up with the it's a quantum, everyone talks about, every government, every politician talks about quantum era. This is a quantum computing, computing is going to change the world. So I want our mathematics community to think of mathematics of quantum computing. That's a major role to play. I was just reading a paper, some of the papers, or guiding some projects on that. So I just came to know that the once the quantum computing starts, all the security aspects like are the cryptographical tools for security is going to vanish in a very short time. So the whole world is working on, just like our Smart India hackathon, there are worldwide hackathons which are working on quantum resistant algorithms. Quantum resistant algorithms can be developed if there is a algorithms can be developed if there is a mathematics behind it. So one of the recent technique which they have developed three methods. One of the method is nothing but the Falcon approach. Falcon approach is quantum resistant algorithm. The one of the leading approaches Falcon approach, Sphinx Falcon. Falcon is nothing but the Fourier transform applied to the cryptographical tools. So there are a lot of areas which one can work on. That's what. So the quantum resistant algorithms can be made provided we should work on the new formulas, new tools, new methodologies, like Coach has said, new formulas, new techniques. Then we can give it to computer scientists to develop the new algorithms and new programming tools. So that is another area which one we can work on. So the third thing is which I would like to see is cross skills. So a new NEP is emerging. NEP some of the autonomous colleges have implemented from the last year. Pune University we are implementing from this year. There are many fears also there. Many opportunities are also there. So it's up to us where we have to go behind the fears or go behind the opportunities. So my third word, the cross skilling. Cross skilling is another word where new education policy is providing. There is no subject barrier. There is no subject. Every subject is that boundary, rigid boundaries, be flexible. So that cross skilling is playing a major role. So your mathematical technique can be applied to engineering. So engineers are looking for financial. They are applying their analytical tools in finance, computational biology, everywhere. So all these area, mathematics play a big role. Financial mathematics is another emerging area which one can look upon. So I have given 5 minutes, so I think I have already used 10 minutes. So these are the some of the areas where my colleagues can work on it. So there are the opportunities are very vast. So apply that touch to the real world problems and give new formulas, new methodologies, new techniques. And the don't worry that the new softwares are coming, but we always will have a role to play. Everyone understands the pattern. So as mathematician we need to make the world aware that where pattern fails, where singularity plays a major role. The logic, how where the logic is essential. We are working on the ChatGPT Copilot era. So we need to work on where the logic apply, the critical mathematical thinking skills, how to question, how to build the logic, where we have a role to play. So this is my give. I mean, this is what I thought of sharing with you all. So the field of I would like to summarize my speech. The field of applied mathematics is very vast and it is continuously evolving with new research areas are emerging, and we need to develop sophisticated mathematical tools, formulae, the logic, and we need to encounter which will be capable of us to encounter new challenges in the emerging new AI challenges in the areas of science and engineering. So that's my advice to all of you. Thank you one and all. Thank you very much for giving me an opportunity, to the entire AI team, to the entire team headed by Coach Sir and Handore Sir and Sani Ma'am and Asha Jadhav Ma'am. Thank you very much, and I hope that you will have a joyful knowledge journey through this 5 days of workshop. Thank you all. Thank you, ma'am. Thank you, Coach Sir. Thank you. And I'm very happy to see all of you virtually. Handoris and Coach Sir, I have not seen you for a long time. Nice. Very happy to see you all. Thank you.
असं आहे का?
हेलो हेलो ओके आई थिंक आप उधर से बोल के देखिए इज इट आई एम ऑडिबल
Yes, yes.
ओके थैंक यू sorry for this technical issue I think I off this video that will be better so first of all thank you thank you ma'am for giving the gracious introduction of mine and thank you for all the organizer for organizers of ISTE approved 1 week online STTP short-term training program on applied mathematics in engineering and science and engineering from 22nd to 26th of July, which is organized by Department of Engineering Sciences, KZ College of Engineering Management Research, Pune, for inviting me as an keynote speaker of this STTP, which will be a wonderful journey of all the participants in learning and doing away. So today I will be trying to enlighten you on the topics of graphical interpretation of mathematical functions in real life and with having some of the basic questions in your mind as a student of anything like as a student of science or as a student of engineering. So I have some of the basic questions that how the mathematical function works, what is the use of mathematical functions in real life, why mathematics is so important to study as a like kids. These are some questions which comes in a mind. Can we live without mathematical concept? Is this mathematical functions seen in our day-to-day life? So let me try to explore you in the journey of mathematics or mathematical functions, you can say, in the real life, and how you can be visualize these things. So things comes, what is the importance of this visualization of mathematical function in real life? So mathematical functions are foundation to understand and modeling a wide array of phenomena in sciences, engineering, economics, and many other fields. The visualization of these functions play a crucial role in translating abstract mathematical concept into practical real life application. So as enhanced understanding, the visual representation help in comprehending complex mathematical relationship by providing intuitive insight. Graph, plots, and charts make it very easier to see trends, patterns, and anomalies that might not be apparent from the equation alone. Number two, the communication, which plays a very role. Visualization adds an effective communicating ideas and findings, whether in academia, industry, or public policy. Clear visual representation of data and functions facilitates better understanding and decision making along stakeholders with varying level of expertise. Number three, problem solving. In this field, like engineering and physics, visualizing function is critical for solving real world problems. Engineers use functions graph to design system and predict their behavior under different conditions. Physics visualize wave functions and field equation to understand to study the physical phenomena. Number third, which is a growing or emerging topic, that is data analysis. So in the data science and economics, visualizing function is essential for analyzing trends and making forecast. Economics use graph to understand market dynamic, while data scientists use visualize to pretend large data sets for identifying correlations. Education and training. So visualizing tools and invaluable in education, helping understand, grasp difficult concept more easier. Interactive visualizations such as graphical calculator and simulation software allow students to experiment and learn through explorations. Innovation and research. So visualization forecast innovation by enabling researchers to see connections and explore new hypotheses. Uh, it is a powerful tool in field like biology, medical medicines, where visualizing functions can lead to breakthrough in understanding complex biological system and disease mechanisms. So in visualization of mathematical concept is a vital bridge between theoretical and practical. It enhance understanding ideas, communication, support problem solving, facilitate data analysis, enhancing education, and drive innovations. So it is an indisciplined tool to leveraging mathematical insight in real life applications. So I just be try to give you a short type of uh, applications where this mathematical visualization is important in a real life application, in a real life problem, and how it can be useful to a layman also. So I believe, I think your my screen is visible to all of you. Screen is visible. Hello, hello. My screen is visible. No, no. Now just confirming me. Now it is visible. Yeah, just a minute. I just okay. I think now it just yes, please. Is it now? Is it visible? Yeah. Okay. Perfect. So uh, good. I think that I try to believe that everyone will do things with me. That it is not like, yeah, it is a visualizing kind of things. But if you do with me, that you, if you visualize in your system, that will be more better and understandable for you. So for this, maybe you, for few of you know, aware, maybe aware about this mathematical tool, which is Wolfram Mathematica, right? Or I will share a link of this. So maybe in the chat box, I have pasted the link of this Wolfram Mathematica. So what you can do, you just be click on this, and you can be join it on the free version of this cloud-based Wolfram Mathematica. So easily you can sign up, as I have sign up for free. You just go as of you are going to explore what the things is work. So this type of signing information it is required, the basic things it will require. So I already signed it, and I'm having software of this, so I work on the softwares, but I just show you the interface of this Wolfram Mathematica. So here easily you can be signed up, and then you will open a notebook. Or those who are not having a laptop with you, so you can be download, it's a Android based application which is also available in the Play Store. So if you type Wolfram Mathematica, then easily you can be get that application. So there you, because whatever the things I will learning, I will learning with you, so you should be do practice with me. So that will be a fruitful kind of thing work. And then by this talk will be useful for you in the real sense. So I suppose that everyone get this link or try to connect. So may I can somebody respond in a chat room that whether did you receive the link, or if you face any problem while signing, then I can be resolved. Or if all are there is no problem, then directly we can go for the presentation, or for this thing, for playing with the mathematical functions. Did everybody? I have posted it. Sign in is open. Yes, yes. Sign in and open the new book, notebook. Right. Perfect. So that will be the things which required. You have to open a new book, new notebook. Okay. So all set. All set. I think. Yeah. So just sign in and then open a new book. Or those who are joined by this thing, by Android phone or this, so they can be do like they can be uh, download a Android application of Wolfram Mathematica, and then easily they can be open a new notebook. So it's a very easy task. So that you, all of you will do the things which I am going to do in my software. As I'm having software, so you can be explore by online on free version of this. So easily when you require, then you can be purchased, or otherwise you can be do lot of things in that. So perfect. Now I suppose uh, Rini, sorry, Sini responded that maybe she opened it. Okay. So now I will come to this. Yeah, just I will show you the. Yeah, this is Wolfram Mathematica, which I have, and now I'm going to open my notebook. Is it visible to all of you? Is it visible? That presentation, just you look, is it visible? If not, please respond me in the chat box so that this slide is visible or not. Is it? Visible. Okay, perfect. Yeah, thank you. Yeah. So we are going to explore these of the few topics in today's talk. So graphical interpretation, we are going to do the some of the functions. So now, firstly, I just bifurcate my talk in some of the graphics points. So first, we are going to make two-dimensional plots. Two-dimensional plot of the functions. Then uh, again we are going to plot in a parametric plots. Then we do some of the graphs in three-dimensional, and we are going to have graphics kind of things in three-dimension, graphics in three-dimension as well as in the graphic. So let first if we are going to two-dimension, so anything anything just like if we are saying about the sine functions, so let we see that how these sine functions behave. Like your teacher, maybe I think it is visible to all of you, or I just be increase the size of the notebook so that it can be more visible. The command will be more visible, right? Or I think, yeah, this way, right? So your teachers will tell the sine function is behave in a sinusoidal way or in such way. So that what is that sinusoidal behavior? So just you type this command in your notebook, that plot the sine function sine x, and in the sine x, or the x is between 0 to 2 pi. We are giving the range of sine between 0 to pi, and then press the enter. Then the behavior of sine function is comes like that. That your teacher, maybe you teach, and the from the schooling time you are listening that sine function is behaving like a sinusoidal behavior. So that sinusoidal behavior you can visualize, you can see that how the maximum range of sine function is, it's a +1 and the -1. The range is lies between -1 to +1, and it makes a perfect one circle, complete circle between 0 to 2 pi in a quadrant, right? So this is a function which behaves, right? Now, did you get the results? Just you plot, give the command of plot sine x, and that will be in this square bracket, and then curly comma and curly bracket x, comma the range 0 to 2 pi. Or you can be give the range of different 0 2 pi to minus 2 pi to 2 pi. Then also let me give you the some other range so that you can see. If I give a range of 0 to pi, or let it be minus pi to pi. So let's see, the behavior is like that, as many have seen that type of graph. So you can be make some of the experiments on the basis of this. So did you get the plot? Did you get the plot? Yes, Vijay Hamle, you can write in the chat box so that I can be read what is your question, or you can ask me, no problem. Okay, so now let we have a plot of second plot of the function x, which we give in the range of minus 5 to 5, and then I express the expressions, plotting of expressions, right? So like this is the straight line, which all we are saying that y equal to x, which is a straight line. So it is a straight line passing through the origin, and then a range I have given from minus 5 to 5. So it label, plot label is x. So that type of function you can easily get in your mathematical stuff. So now similarly, if I put x instead of x, if I put x square, then the graphical behavior is like a U-shaped curve. So you can see that the graph of x square is shown like a U-shaped curve, and where we get we can be analysis many things. So now similarly, if you increase the range of power, increase the power of x power 3. So with the I just increasing the power of x and the plot in the same range, so I can see the behavior of my functions. It is xq is in the first and third quadrant, it is behaving like that with the same range. Now if I am going to plot is some different kind of function, which you can say it's a tan function, because sine and cos have the similar behavior, but the tan function have a different behaviors. As you by having the values of tan, we get to know that how this function breaks. So if we give the command of plot tan x, and then range we decided from minus 3 to plus 3, then the function seems like this. So it shows the discontinuous behavior of this function. That you can see that this sin x, tan x is how it behaves, and by seeing this graph, we can be analyze how this function is discontinuous. It breaks their continuity at this point, and after a certain time, certain interval, it start behaving. So you can have a look that this function is symmetrical about the origin, and it is pass in the lie in the first and third quadrant, and for the second or fourth quadrant is its behavior is let's say it will be on somewhere 0.8, and from minus 0.8 to 3, and then similarly minus 3 to somewhere 8. So in such points it will behave. So if I put this function, the same tan function, but excluding what minus pi by 2 and pi by 2 behaviors, so it is also showing the same type of graph, because if we are saying minus pi by 2 and pi by 2, so that is minus 90 degree and plus 90 degree, that type of behavior comes in the graph. So by having such type of graph, so we can be predict that uh, how our functions behave in particular domain, in particular range. So not only this, let we explore some of the things in a different way, and how we can be change the functions and with the different commands. So like you have a different colors automatically be used for each functions, right? So now I I am plotting two functions simultaneously, or these two functions are like plotting sine x comma sine 2x with the range of x is 0 to 2 pi. Just I enter it. So you can see the behavior of this will be the sine 2x, which is in orange, or in the blue it will be sine x. So you can see if I increase the magnitude of this to magnitude of angle, so it will, the behavior will be changed. So we can plot two functions simultaneously. So now if I plot three functions simultaneously, so let with the same range, let we have seen that this blue line says the sine x, and then orange line is the sine 2x, and then green line is of sine 3x, the behaving nature of the sine function. But the when we increase angles, multiple of angles, so behavior will be changed and the plotting will be changed. So if we use the plot legend expressions, the command of plot legend, let's see how the things will be changed, or how we can be make it useful, more useful. So there, if I used like the command with plot legend, so there you can see, just I plotted sine x, sine 2x, sine 3x with the range of 0 to pi, but I use the command of plot legend and in the expression, so that it will shows the which graph is for which function. So let's, you can see, as already I have told you, that the blue is for sine x, orange for sine 2x, and the green for sine 3x. So it shows like this. Then similarly, labeling of each functions, right? So if we labeled each function with the command of plot label expression. So here we plot sine x comma sine 2x. You can have a look that these two functions sine x and cos x with the range of 0 to 2 pi, and their behavior is, both the behavior is sinusoidal, but the difference is difference of pi by 2, right? The peak where it start from 0, and cos x start from 0, sorry, cos x start from 1, and then sin x start from 0. So the behavior is like this. So here we can be labeled where will be the function. So by using plot label expression command we can be used. So I think till now, if anyone have any doubt, because we are just going slowly, so you can be put in the chat box, or you can be maybe you can ask directly, or you can ask at the end, that whatever will be the possibility there, I have no problem. Yeah. So now if we filling a curve, filling a curve, so let's have a command that filling bottom curve. So you can be fill which, if we are using area under the curve integration type of things. So this is a function which can be more useful. Yeah, this is the graph which can be more useful, where student get to understand which part of the area we said we are saying that this curve is area under the curve. So here I'm giving a plot of 2 sin x plus x with a range of 0 to 15, and I fill the bottom part of this curve. So my curve seem like this. So by using a simple command filling bottom, it will fill all the regions, the bottom side or top side, whatever behavior. It will be top side also you can be filled, or bottom side, as we have already covered. And now filling between two curves. This is also a application of area under the curve, where we have the plots of sin x plus x by 2 or sin x plus x. This is a plot of these two functions, and we are plotting it between 0 to 10, and we are saying that we filled. Now we give a different type of command because we want the filling between these two curves. So now the command is changed, filling 1 to 2. The filling will be command by this, a filling arrow and then curly bracket 1 arrow then 2, which means from 1 or 2 the filling will be between curve 1 and curve 2, so that you can be easily find this area. So this is very pictorial kind of things. So directly it can be used in area under the curve. Now, where if we use this type of functions, right? So here we use Bessel functions, and we give the values of Bessel n to 4, and then x between 0 to 4. We give the range of x 0 to 4, and then we are filling x-axis. We are filling the axis. So this is a table of Bessel's functions which will be evaluated, and here we get the different type of functions with the filling plot. So now, if we have a function of sin 10x or sin x, so you can see the behavior of sine of 30 sin x seems to be like a magnitude behavior. So similarly, if we plot a function of 1 by x, so here if we plot a function 1 by x between -1 to 1, so the behavior is shown in particular range, how the curve is behaved. So by seeing this graph, you can find the limits and then continuity of this function, as well as you can predict whether this function is differentiable or integrable. This type of things you can imagine, you can evaluate. Now, if we give a range of, this is square t root of x, and then x is lies between -1 to 1, so the behavior is seen to be like this. And now if we come to flooring these functions, so like root 2, so we are learn step functions or stepping of functions. So the behavior of flooring, if we give the command of floor square root x, So that x lies between 200. I think someone is. Hello. Someone is audible. Kindly mute yourself. Yeah, I suppose it's okay. Okay. So now, so if we are giving a plot for step functions, so easily we can be plot this type of function. So this function is like a piecewise continuous or flooring of function, yeah, or we can say it is a stepping functions. So we can make this functions. Now if we are using that floor function but with the special command of exclusion, so like if we are using the command of exclusion none, so you can be see the draw is the graph is connected. So here it's this this graph is seen like a stepping of functions, or it is a stairs, one type of stairs seems to be. So here we can be predict that function is how it is continuous, how it can be it is behaves like a piecewise continuous function. So now if we use some special command to draw a grid functions, so now here if we give the grid function plot of sin x, which is between x is lies between 0 to 15, and then plot point we are consider pp, then next regression mr, and then we are giving the range of mr between 0 to 0 1 2, and then pp is like 5 to 10. So here we have a different type of behavior of this grid table of sin x, where the behavior lies between 0 to 15. So you can have a look on that. So now if we use a plot range of two functions, so now here we can have a function of two different function. That function is x ki power 4 minus x square plus 2, and then x is lies between minus 2 to 2, and then the other function is x power 4 minus x square plus 2, and then range is also that like. So the plot range which I set is 0 to 2. So you can have a look. There's this type of behavior is seen in two different plots. So now if I scaling function, I scale the function. So if I use gamma z, and then z lies between minus 4 to 8, and then scaling function is log x. So the behavior of this log x function is seems to be like this. Now if I use a different kind of command, that expect ratio, so how these two functions is behave. So expect ratio, by using this expect ratio command, we can be plot similar kind of plotting, or if we want two or more plots, so we can use this expect ratio. So here I use the command for the function root of 1 minus x square, and then x is lies between 0 to 1, and then again function is 1 minus x square, and these are the same range, but the expect ratio is automatic. So here I get a two different plots, two different kind of plots which can be based on the expect ratios. So now if I use a command for axis, and axis if I am not giving I just want to give a behavior of function, and I don't want to give the axis. So here I can use a function, sin c function, where I use the command for axis false. So there will not be any kind of axis. So the function behavior of function can be seen easily. If I just want to draw a y-axis, so I just give a command of plot sin c x, or giving the range of x 0 to 10, or axis I use axis false and comma true. The second x-axis false, that's why axis is not presented, and the y-axis for y-axis I have given the true. That axis will be seen. So you can have a look that y-axis is shown, but we are not having x-axis. Now, if I want axis labels, so here I can be use the different command, but axis label automatic. So whatever we are plotting two type of two-dimensional plots. So we are having the graph of we are having x-axis as well as y-axis. So you can have a look that plot sin c of u, and where the u is between 0 to 10, right? So now the axis label is we set on the automatic. So for specific, if I want it to change axis, or I just be mention a specific axis, so I just be use the command of plot sin cx, and then range I have given axis 0 to 10, or I want the axis label is x, or my function, right, sin cx. So you have a look that this is y-axis sin cx, and then the x-axis, it is x-axis. So you can also manually, if you have different kind of variables, or you want to plot and you want to plot between these two variables, or independent variables plotting, so you can be plot as well as you can be labeling them, so that the graphs seems that this is a relation between these two kind of functions. So now if we determine the axis origins, so now you can have a look on the function where I just give a command for plot of 1 upon x minus 1 plus 2, and then xi variate from -2 to 4, and axis I put on origin, and this is automatic. I'm not giving a particular kind of axis, but it will be origin set I automatic, so that I have get a origin from the actual origin, right? If I try to shift my origin, so I can be give a command of this type, so that my origin gets shifted. I give a command of axis origin is axis origin 1 to 2, right? So if you have a look, then you can see that x-axis is at 1. This place intersecting point is 1 comma 2, and this is the x is 1 and y is 2. So the origin, it will shifted, like 0 0 is shifted from that place. So behavior can be more visualized compared to the last one. If we are going the back, so it is crossed, the graph is crossed, behavior is crossed at 0 0, right? But now we shifted it to 1 to 2. So by using this axis origin command, you can be shift slider your axis also. So now if I use the axis style, so by using axis style, so you can have a look on the command that plot the same command as we are earlier using, plot sine cx, and then range is s0 to 10, and axis style, this I have added the new one, axis style arrow, and then directive thick dash red and then blue. I am also giving the command type of axis style, how it can be thick dashes. So just I give thick, so thick will be for this one, for the graph plotting, and now dashes dash or red will be for x-axis, right? Dashes and red, and this thick blue for the y-axis or the graph. So that you can be there is you can be easily identify which axis is this representing for this type of function, or which axis is representing for the different kind of function. So now just I give a plot of like Bayesian baseline position axis. So you can have a look that if I give a command of baseline axis, so it will be a thick or broader function have to be seen, or this is a plot of zeta function with a real part or imaginary part of this. So as we have imaginary, this is the imaginary part of zeta 1/2 plus it, and then the real part of zeta function, or with the range will be same. So the behavior is shown like that. So now if I am clipping the two functions, so if I use the command of plot sin x upon x square, or clipping style is I put none, right? So if there will be no clipping style, so we have the clipping style automatic. So you can see that how the function is behave, like what is the this thing. So here you can clip the where will be the function is shown, right? So by using the clipping, if you are not able to identify the function behavior, how the function, where the function is on which point, so by using clipping style you can be get to know the exact value of the functions. Now if we want to this do the clip in a different colors, so we can use the different colors, the clipping red, blue, whatever you want, you can be clipped by using this command. So now if you want to do the clip red and thick, so here I just we put the clipping on red and thick, right? So now if we do the clipping on upper side, so yeah, both side you can say, so the clipping red and thick, right? Okay, the same function, but we use different clipping style, so that the behavior of function is seems to be different or more visualized. So now if we coloring the functions, if we are going to color the same functions, but if we are using the different kind of colors, different kind of uh, coloring and styles, so you can have a look that function is by using this color function, colors a function x y, and the hues of y, right? So functions coloring is different. Both the function have the different coloring, and the same, this is the same function and it shows the same behavior, right? So now if we use coloring function in a rainbow or dark rainbow, so you can have a look that plotting the same function, but we are using a different command for color function dark rainbow. So it behaves a particular behavior where the function graph change and then color will be changed automatically. So now if we have a coloring function false and plot thick, so here like we give a command of specifying that color function where color of xy, but if y greater than 0, the behavior like y greater than 0, so that will be red, otherwise it will be black. So coloring function will be false, plot style will be thick. So have a look that function when the y value is greater than 0, the function is red, or when it is less than 0, less than or equal to 0, then it is red. So this type of graph we can be used by specifying different kind of plot where we are specifying that this function behavior is changed between this point to this point. I think, sir, someone have, yeah, I suppose it is, okay. Okay, now we can use filling x-axis, right? Axis we can fill. So the same, we are using the function, the sin x between 0 to pi, and then color function is xy, and then we fill the axis, filling x-axis. So you can have a look that we fill the axis, and then we have a plot of like this. So yeah, we have very short limited time, so little bit I am just going little faster, and then I will show you give you this file to all of you so that you can be run in that mathematics also. So it will be useful for all of you to have a to play with this graph. So here also we give the style of this thing, rainbow type of style. If we color function scaling, if we give a plot of this plot of table sin 4x, so here we use the plot style thick function, color function function xy, use color functioning scaling cf, and then this is false and true. So we get a plot of sin 4x, which will be same as sin x, the behavior of sin x, right? So now when color is the function is same for red and black, yeah, it is. This is the same for different colors. Now we are using epilogue, the command for yes. So by using this command, we can be give the intersecting point where this graph, the function intersect with the x-axis. So here you can have a point size. We have a point size of 0.04. We put it. You can be increase or you can be reduces. And then point is 0, 0, and then pi 0, and then 2 pi 0. So we give the points where it is epilogues, where the intersecting points we want to show. So it can be shown in many of the graphical while we are teaching or learning. So this is the flooring functions which already I have used, but there this type of function is piecewise continuous. You can have a look that how this function is break their continuity or at 1, but it is also starting their continuity at 1, but the value is 1 1. It break at 1 0, but they start from 1 1, right? So this type of plot we can easily receive. And then evaluating monitor, so like if we have a sin x, just a minute, log, yeah, yes, evaluating this, and then evaluation of, okay, the sin x and filling the plot of, yes, if we want to give a plot of this list plot data filling, so we can have, we can giving a command of the sin x function, and which is the which will be filled by this filling command. So now if we uh, want to count the evaluation point, so here we can have a look that evaluating point is 431 points evaluating in this graph. It is used, 430 point is used in this graph. So now if we are using exclusion, so already you have a look that there's a step type of function flooring of x square, and now if you want a exclusion comes from a branch discontinuity, so this is the graph of imaginary square t, which is a discontinuous kind of functions. So now if set of exclusions, so the equation where we have a equation that 1 upon x cube minus x plus 1, and then the plot range is -2 to 2, and then exclusion, if we exclude these points, so the graph seems like this. If we two set of exclusions, so there you can have a like function of two set of functions, right? 10x cube minus x plus 1 plus 1 upon x plus 3 e to the power x, and the range is -2 to 2, and then exclusion of cos x cube minus x plus 1 or x plus 3 e to the power x equal to. So if we exclude this function, then the behavior seems to be like this. So we can be use such type of plot while we are giving we are making integration under the curve. So now if we have a flooring of function, so this is a 10 floor of 10x, where we exclude the sin x cos x, where cos x equal to 0, we exclude these values, this graph, and then we get the behavior of flooring type of behavior of 10x. Now these are the two-dimensional plot which we have seen till now. And now if we have a parametric plot, so if we are saying about the two-dimensional plot, so that if you are plotting two-dimension kind of things, so it can be easily that you can plot or evaluate, so that your function, how the function is behaving in a particular range, particular domain, it is easily seen. So now if we are going for the parametric type of plot, so here if we using parametric plot of sin u or sin 2u, so we are giving the same range of 0 to 2 pi. So we can have a look that function is behave like this. It is behave like this figure of 8, we can say. It is both the function making figure of 8 kind of things. So if we having a parametric plot of a r square, root t, cos t, and sin t. Root t, cos t, sin t, and then t is from 0 to 3 pi by 2, or the r is 1 to 2. So we can have a look at this behavior. So how our parametric function is seems. And I think all of you know that parametric function is such type of function that they are in it third function. Like if x is dependent of u as well as y is dependent of u. So this is the we are plotting the behavior of x as well as y, which is dependent of u or t other functions. So here we have seen that the first function, which is a function of t, and then second function, which is also a function of t, and how these two functions behave like this. So similarly, if we use the command of this parametric plot of this different plots. So here we have more than is a 4 functions we are using. That is 2 cos t, 2 sin t, 2 cos t, sin t, cos t, 2 sin t, and cos t, sin t. So these are the 4 functions which we have plotted, and we have given the range of t 0 to 2 pi, and then plot range, plot legend is expressions, so that you are not going to confuse that which function is which one. So it shows that the blue one is 2 cos t, sin t, and then orange one is 2 cos t, sin t, and then green is cos t, 2 sin t, and then red is like cos t, sin t. So these are the 4 parametric functions can be shown in a one plot. So now if we overlapping these functions, so there is also a elliptic type of curve. So parametric of r 2r cos t, r sin t, or either, the other one is r cos t to r sin t, and the range is 0 to 2 pi and 0 to 1, and we fill the mass plot, right? So these type of plots, you all of you maybe used elliptic ellipse, two different ellipses or parametric. These are very famous conversion equation for parametric equations. So easily it can be shown by using this parametric command. So now if we are going to have a simple parametric in a straight line, so these are like two parameters, that 3u plus 4 or u plus 2, and then it makes a u plus 2, so which is seem to be a circle, a straight line. And now if we use the command for cos u comma sin u, and then the range between 0 to 2 pi, so this parametric graph is shown like a circle. So if we use the function of 2 cos u comma sin u and having the command of parametric plot, so we get a ellipse with the range of 0 to 2 pi. So easily, and then if we use the parametric command of cos u, sin u, and then we change the range u pi by 4 and 5 pi by 4. So this is circle segment we are having. So now simply we just changing the range of the this u function, parametric functions. So now here if you have a look that the same function 2 cos u sin u, but now this time we change the range of this function, that is pi by 4 or 5 pi by 4. So it seems to be a ellipse segments. And if we use the command of this parametric command, or we can have a filling of this. So like it is a rectangle with the command of uv, that u x-axis and y-axis is u and v, and we fill u with 1 or 3 or v 3 and 4. So the region is filled like a it so seems like a rectangle. Now if we are going to make a disk, so there also we can use a command of v cos u, v sin u, where the u varies between 0 to 2 pi and v varies 0 to 1. So it seems like a disk, because this is the circle in 3 dimensions, so which will be a disk. Now then we have a ellipse. The solid is ellipse we have by using the command or the function 2u cos u, v sin u, and then u variate 0 to 2 pi and v variate 0 to 1 with the command of parametric plot. Now we have a disk sector. So if we change the range of u 0 to pi by 2 and then v 0 to 1, then we get a disk sector with the function of u cos u, v sin u with a parametric plot. Now if we use it, we want a disk annulus, then we can be plot by v cos u, v sin u. So u is between 0 to 2 pi and v v 1 by 2 to 1, right? So this is a disk annular. Now if we want disk sector, so we can be use the v cos u, v sin u, and then u can be variate 0 to pi by 3, and then v will be half to 1. So this type of disk annular we can be received. Now if we want a rotated ellipse, so like you have a figure of rotation of this ellipse, so how it can be rotated with the angle of 30 degree. Right? So you can have a rotations, that is pi by 6, pi by 3 and pi by 2. Okay. Now this disk is slightly rotated. Is the firstly it is at axis on x-axis, and then it is slightly rotated by pi by 6, then pi by 3, and then pi by 2. So the rotation is seems like this. Now if you have a rotation transform of this function, so this is a parametric plot of 2 cos u sin u with a range of what, u theta 0 to 2 pi, and then theta the angle. This is rotation transform. We are evaluating rotation transform of theta, where the theta is also 0 to pi by 2, and then we are using the command of mesh automatic. So it is filled by mesh command. The region is filled by mesh command, right? So if we have a yes, right, if we have a right, so this is a like we are giving two parameters, x is cos u, sin is y is sin u, and we are having a circle. So this is parametric plot of what, u cos u sin u with in a circle, right, in a form of circle, right? So if we have a plot of the function that is sin mu sin nu. So this is also parametric graphic grids which can be seen
नाही लागणार लगेच
in the
आधी प्रायमरी इन्फॉर्मेशन
graphic
देते
grids which shown in the parametric plot of sin u, right? So if we have a parametric plot for Nyquist curve, so just you can have a look. Then here we have Nyquist curve of h equal to 1 by s minus 1 by 2 square, and then we are backslash. We are expressing, this is expression of iota and iota omega. So we get a function of this kind, and we are plotting this parametric plot of this function with the real and imaginary part of omega. So the range we have given 0 to 2 pi. So now if we are having some complex mapping, so we can be use table of parametric plots. So here we having complex type of function which can be real plus imaginary, and we filled this. We are using the math style where orange and green we are using the grids, and then plot is range we are using, and then with the different values. So here we can have a look on the different kind of plots, and how this parametric, this will be the real part, this will be the imaginary part, and this will be the combined part of this parametric plot. So here we can be visualize that such certain type of function which is a real and imaginary can be visualized. So now Jawkins plot, have a look. So this is also a complex type of function which is shown in the figure. Where the real and imaginary part can be easily shown. So now we plotted, but the thing is more if we are coming for the graph in a 3-dimensional, so it gives more solid effects. That now we are plotting all the graphs in the 2 axes, that is x or y axis, but we are not using the 3rd axis. But if we have a 3rd-dimensional type of plot, then the behavior seems to be perfect. This is some surface kind of things we have shown. So here I am using simple command of plot 3D, where my function is sin x plus y square, and I'm giving the range of x is -3 to 3 and y is -2 to 2. So here I can be, if I can rotate and I can have a look on this function, that how this function is behaved, what is the behavior of this solid layer, you can say solid layer, how on which surface it behaves. So we can visualize it in a very easy way. So in this quite like in the fast way, let me have a look on that.
जाने की भी शुरुआत करते सब लोग.
Okay. So now just we have a 3-dimensional plot of x square y square, comma, the other function is minus x square minus y square. So here we get a layer kind of thing. So if we want, then we can have a look that this function is behaved in a, this function, the function behavior of this function is not only one, the one surface, the x square plus y square is the upper surface, and minus x square minus y square on the lower surface. So the behavior of this function is easily seen in the plot. Just we are giving the command of plot 3 dimension, and the curly bracket we give the functions, both of the function, and we are giving the range of both the axes, that is x-axis as well as y-axis, right? X-axis, y-axis from -2 to 2, or if I change the range, you can say 3 to 3, or here also if I use, then also the behavior will be same. It will be changed. The behavior will be same, right? So color function I use rusty tunes, so you can be change the color function also. So now if I restrict the domain, right? If I restrict the domain, so here I just having the functions that with x square plus y square, comma x square minus y square, and the same range from -2 to 2, but the region which I am going to plot is region functions, function x y z, and I'm giving the restriction that x square plus y square less than equal to 4. The function the behavior between the function behavior between less than equal to 4, and box axis automatic. So my plot is shown like this. So this is a graph of x square plus y square, but with the restriction of it should be less than equal to 4. So the upper plot, the positive side of plot, we are seeing the graph of x square plus y square, and then lower seems to be minus x square minus y square. We can, even though we can rotate it, we can have a look at how the function behave on which particular points, or the other side also. So on on such way you can visualize the behavior of this function. If we change some let we change if we change some restrictions. So if I increase, let's say the range of this, and if I increase the restrictions by 10, so let's see what type of function we get. So let you have a look that I increase the range which is 5, this one -5 to 5, so this type, and I restricted that the function will be less than equal to 5. So the length of the function, the curve is increases. It is the surface is seems to be like, but here it is less than equal to 4. The curve is up to 4, and now it is up to 10 with this restriction. So the different kind of things we can have. So now the plot with the branches. So now you have a look that this imaginary part of sine inverse x plus iy square k power 4, and then range of -2 to 2, and y is also -2 to 2, and then mass none, and then we have the behavior in a yellow color or the white. So you can have this is the branch cut of the function. This plot is for using branch cutting of this function. So here we can have a look that this function is used like this. So now if we are saying about the application of three-dimensional plot, so like if we plot a function of x square plus y square, where the with the equation of e to power 1 minus x square minus y square, and then xy is giving, and we are using the plot point 50. So here you can be have this type of mass plot we are having. So we can be analyze the what is the depth of this curve. So if we are seeing this curve is having depth inside this, or if we are having a look, so this is the curve point we can be nodal point we can be seen. So similarly, if we are having a mesh setting, so that the same plot, but the different command of mesh setting. So this different setting of plot is soon. So again here we are using some specific mesh setting, three type of this. So here you can have the mesh setting automatic none, and these are the plot which shows that how your function is behaves. So like if we are giving some plot of, yeah, this function already we have plot, but here we are not giving any restrictions. So this is the function where less than equal to, this is x square plus y square, which can be less than equal to x square minus y square. So the behavior seems like this. So if we are setting this type of functions, so even though we can be plot the norm functions, the norm of x, y, which is used in real analysis or this one functional analysis, the norms, or sometime in the real in the linear algebra also. So here we can be use the norm functions. Here you have a loop of norm function, norm xy1, then norm 2, and then as well as norm at infinity. So these are the colors which shows the different setting plots for the norm functions. So now if we set this norms behavior of x, norm x 1, norm 1, norm x2, x3, and then x infinity. So you can have that how these norms behave, how this surface changes from their definitions. So these things theoretically you have already learned, but graphically you can have explore this type of behavior shown. So now if we give a saddle surface, so this is a plot for y square minus x square, and then x is lies from -4 to 4, and then y is also lies from -4 to 4, and mass function is 3 type percentage, and then we have this type of saddle surface of the curve. Now if we having a normal function, and then we are going to create a limit of these functions. So this is 10xy and x 2x square plus 3y square, and then x is y is similarly lies between -3 to 3, and then region function is xyz, and then we give a restriction of this function, the 2x square plus 3y square greater than is half. Then we put a certain limit, maybe some of the function, if we do not, if we give a limit, then the behavior sounds more clear. So we can have look on such type of functions, right? So now if we have a real and imaginary part, as already we have seen, so here the real and imaginary part, but the behavior in the this thing you have seen in parametric curve plot, but you can have a look in the three-dimensional plot. So this type of function is we can have sine x plus iy and imaginary part of x plus iy, so the same range, and then the behavior is shown like this. So if we have a complex different complex components, so here you can have it different plotting of these functions on different behaviors. This is very simple function, that's sine inverse x function. So now branch cut, if we are having a branch cut of the functions like this. And then here, if it, right, so you can have a look. I am giving a table of plotting. So this is imaginary part of sine inverse x plus iota y cube. Then similarly, imaginary part of cos inverse x plus iota cube, and then sec, and then cosec, tan, cotec, tan inverse, cot inverse, sine hyperbolic h inverse x, cos h inverse x, and then sec h inverse x, cosec h inverse x, and then tan h inverse x and cot h inverse x. So you can have a look that the behavior of different functions is seem to be different. Some, if we are comparing the behavior of sine or sine inverse and cos inverse, then it is also a different type of behaviors. So we can simultaneously plot number of uh, functions. If we are comparing, have a comparison between the functions. So this type of plot we can make. So similarly, I am giving here a tabular plot of these functions where sin x, cos x, sec x, cosec x, tan x, and then cot x, all trigonometric function and their inverse of the trigonometric function, as well as I am giving the hyperbolic functions and their inverse of this. So 6 is trigonometric, 6 is inverse of this, then hyperbolic 6, and then this. So it will be 24 plots we are having. So you can have a plot of 24 functions, and then plot range is between -2 to -2 to 2. So here you can have a look that how this function behaves in a particular range. And if we are talking about the in the complex, the nodal function, nodal root, or the complex roots, so you can have a look that how the behavior, surface behavior of this function shown. So these are the functions that we can easily visualize. So now I just be having the parametric plot, the very quick, we just go the parametric plot for three-dimensional functions. If you are having the parametric functions and how three-dimensionally how it look like. So you can have these are the two functions, that is cos u, sin u, cos u, and sin u plus sin v, and then sin v. Three functions we are having, parametric three functions. So the behavior is like this. Okay, and now if we are having the single two functions, then the three-dimensional plot is seems like this. And then multiple parametric functions if we are having, so it's a two type of rings shown in the plot, right? So now if we are using a parametric plot for styling, right, so this is the parametric plot of two function, that is sin u sin v plus 0.5 cos 20v, and then there are three plots, and then cos v sin v plus 0.5 cos 20u, and then cos v. So the we variate the range of -pi to pi, and then v minus pi to pi, right? So these are the gridding function we are having. So now just you are having the plot of this type of plot. Sir, how much time I have? Sir, Ma'am, how much time I have? I complete it? I think I need 10, hardly 10 minutes to complete it. Hello, hello. Is it anyone? Hello, sir. How much time I have? Okay, I try to wind up within 10 minutes. Okay. Yeah. Yeah. Thank you. Thank you. Yeah. So now we I am just having some of the applications of this. Sorry, sir. Are you saying something? Hello. Okay. Okay. Thank you. Okay. So now, if uh, yes. So now, if we are having some parametric type of functions, so just I'm making a simple plots. Yeah, you are having a surface three-dimensional plot of these two parametric functions, or easily we can have a cylinder type of this thing. We can make a cylinder by using the parametric functions very easily. Even though we can make a cone of the functions by using the parametric functions by very simple function of u cos u and v sin u and to v, right? And simply we can make a sphere of the parametric plot in 3 dimension, as well as we can make a ellipsoid of the 3 dimension plot. Not only this, we can also make a torus by using this parametric command of 3 dimensional plot. So this is the Mobius strip, which most of the mathematicians know. They maybe have work on this Mobius strip. So this is also we can be easily visualize. Now we have Kalin Motel. So there, this is also easily we can be plot on this type of Kalin plot bottom right. So easily we can have a this type of plot, which is small use cell growth structure we can be used. So now that we can have simple plot, this cos u sin u, but in a 3 dimensional view we can see then how the function behave, and this is the same function, but some boxing we are using. Or if I use together these two functions, so it behaves like it is together comes and seems like this. So now I am using n for many minimal surface, and this minimal surface can be seen by having this graphical view. So now this is my favorite one, where we are seeing the graphical things. So let we go some fast, because we are having very limited time. So that you can have a look that these circles we have plotted, rectangular, and even the triangles we have plotted in this graph, and the very basic commands we have used. And similarly, if we use it, yeah. So these are the molecular structures you can have the graph of molecules or trees, you can say. If you graph theory you are going to learn or you have learned, then you can have a look of this graph theories. So now we have this the color sunset, this type of function. So it is shown the behavior of this function in particular range, the vibration kind of things which we are seen in some of the water levels. Now if we complete yeah, we can have a networking graphics also. We can have visualize that neural CNN, that neural network systems. So there you can be visualize this, or if you have studied the graph theory, or if you are going to study, then you can be visualize how this network can be connected. Or it is more applicable in the engineering type of things, where you can be easily use these points, and by using these functions you can be make your own network type of thing, this thing. Now if we have a display analogous clock. So I am just making a command for having the this analogous clock. With this command you can see the exact time is shown in this analog command, and it is also running, so you can have look. So not only this, so many more things we can do. These are the circles. These are the graphical circles of cos 2 pi t by 20, comma sin 2 pi t by 20, which zoom in the graphs. So now if I show you some of the interesting images, which can be, you can easily simply code it, make a command, and then you can run these things. So this is the three graphs of 3Ds, which is a cylinder, then a rectangular, then a surface, and then the this polygon, the cuboid, line, and then a sphere. This easily you can be make in a one simple command, in a single command. So now if you are having a function of sin x and sin x and y, so these are the graphical view of sin x and y, which we are easily shown. If we have a function of this type of torus, already we have seen, so we can have a look. Then we can make a graph command of is a decahedron iso. These are different graphical graph complex sizes, which easily we can shown. So now you can have a look, 3D graphical look on the sphere with a very simple command, as well as you can make a graph of three-dimension plot of this contour plot of the function cos u sin y plus cos y sin u plus cos z sin x, and then with a range of minus 2 pi to 2 pi, and the same range. So here I think it will take a little time. It is running because sometime it will be a contour plot. So here you can have a look that contour plot is seems a very different kind of things. So yeah, yeah. So yes, have a look that this is the contour plot of this function. So here we can try to understand what type of contour surface it is, or the behavior of function is how the function behaves. So you can be like, you can also plot in different type of thing. This is a spherical plot of 3 dimension. So how this function plotted like this. Now, not only this, the even though you can be use chemical structures. So here I am just giving you a this chemical data, this the structure of molecular plot of caffeine. So I suppose it will take a slow little time. It is, yeah. So you can have a look at how the, yes. So this is the chemical data and how the bonding of this caffeine is molecule of caffeine is seems. So easily you can be understand not only the mathematics but also graphical things of things can be plotted in visualizing the physics chemistry also. So now I have a torus knot. So we have so many problems in differential kind of things, the application of this torus. So the torus can be seems like that. So now I make a cow geometry of cow. So here you can see the visualization of cow seems as we already seen. So this is the graphical things you can show. So and not only this, we can import some of the images from the Google by using certain commands, so that it can be used. So these are the graphic type of things which we can have. Like I import this using simple command of import, and I just be importing this rows. And these are the some. So this is just have a look, because I importing is not a big task, because you can import any image and it can be you just run it. So now I run 2-3 things, then you have a look, and then we are going to conclude it. And then yeah, the cube is so this type of image we have import from rcsb.org, and yeah, these are running, and this will be a graphic. Yeah, this is the command which are we used for RCB. Yeah, so this is the geometry of 3D stand for bunny. So this is the bunny which we can have a look. So yeah, you can make this is not importing, this is the command. You can run it, so that it gives you a bunny shape, the exact bunny shape. And this is a small uh, geometry of creature kind of things which can be shown. And the lastly, this RGB color cube we can be make by using this type of coding. We are giving this type of coding. So I hope you all of you enjoy this journey playing with the graphs, and thank you. Yeah, anyone have the question? So I am ready to resolve it. Please. Yeah. if anyone have any questions, then please, you are most welcome to. Yes. But the thing is, my is simple suggestion or request to all of the participant that I will provide this slide to you that you can be explore, but that you have to go to the Mathematica that already I have shown the free version. You have to take the commands and run it, and then you can easily visualize what type of function you want. Then you can play with that function, so that you get to understand how the function behave and how the beauty of mathematics seem in real life. Because while I am starting and I have few of the questions, then what is the use of this mathematical function in real life? But maybe some of them you get the answer that uh, everywhere we can see the mathematics in our real life, because mathematics is nothing but a language of nature which is written by nature, and we can visualize it by using certain softwares, and it has a very beautiful kind of understanding and awesome. And of course the engineering aspect, it is directly connected with the mathematics, is directly connected with this engineers. So if someone think that without mathematics you can live, so it is not possible. Even though you are not using mathematics directly, but indirectly you are using lots of mathematics, which the engineers or the mathematician are studying in a conceptual ways. But you maybe are not you are just using, but you are not knowing the history behind of that particular concept. So one of my suggestion for all of you, that kindly use these commands and run it, so that you get to explore yourself, not only understanding, but some of them if are working in the research, so they can be explore their research in this thing, in this area. Yeah, thank you. And uh, sir, anyone have any question? Thank you, thank you very much, ma'am, for inviting me and giving me an this. Is there any question? Yeah, I will share the this PPT. Yeah, surely. Oh, okay. Sir have shared you all of you a feedback link. I think feedback link. Yeah. So yeah, Vivek sir, I will send you my presentation. Okay. You can share with all the participants so they can be explore themselves, right? So uh, thank you all of the organizer of this 1 week sort STTP for giving me an opportunity to speak as a keynote speaker for this 1 week STTP. And especially thank you Vivek sir for inviting me and sharing my thoughts for all of you in front of all of you. So thank you, sir.